Hello, everyone, and a warm welcome to what is a rather chilly afternoon here in Lausanne. My name is Sara Bonella. I am Deputy Director at SICAM headquarters, and it is my pleasure to play host for you in this fifth installment of our Mixed Generation series of webinars. Today, we're going to tackle the very broad topic and very new and exciting topic of machine learning. We have three speakers joining us for this first part of the afternoon: Michele Ceriotti from EPFL, David Peter Kovacs, University of Cambridge, and Yasemin Bozkurt from the Max Planck Institute for Polymer Research. Now, we have an interesting afternoon ahead of us. I am just going to steal a couple of minutes from you to share some instructions to make sure that things go smoothly and that we can all exchange profitably this afternoon. So let me start by sharing my screen. Here we go. Oops, no, we don't go here. That's a different screen, sorry. Okay, so the first thing that you should know is that we are recording this session and that tomorrow or the day after tomorrow, this will be uploaded on the SICAM YouTube channel. That also means that if you have to leave at some point, or for those of you who cannot, really follow everything today, you will have a chance to catch up with our event. Now, the webinar is divided into two parts. We start from an extended talk by our first speaker, Michele Ceriotti, and we are going to implement something that has worked well in past sessions. So for this talk, you will have the opportunity to ask specific questions as Michele speaks. But while he speaks, we ask you to ask these questions by typing them in the Q&A tool in the Zoom. Then I will read them and relate them to him as he speaks. When he concludes the talk, then you will again have an opportunity to ask questions. But this time, all you have to do is type in the Q&A and inform me that you want to ask a question, and then you will receive an invitation to unmute your mic, and you will be able to ask the question directly to Michele. This will facilitate exchanges and going deeper in the exchange if it is necessary. When we move to the second and third talk of the day, these are shorter talks, so we will ask you not to ask questions during the talk, but at the end of each one of those, you will be able to do so. And again, all you need to do is type your name or signal your intention to ask a question in the Q&A, and you will be invited to unmute, and then you will have the possibility to ask the question in person to our speakers. Okay, you will not be able to use the video in this webinar at any time. And as I mentioned before, we will invite you to unmute at the moment in which you want to ask a question. Otherwise, you will be muted for the duration of the session. We do not have a chat facility active now during this session, so use the Q&A to communicate with us and with the speakers through me during the first talk. At the end of the third talk, I will explain a little bit what happens after the webinar. We have a poster session, and this takes place using Gather Town. So those of you who do not know how that works, please stay on, and I will try to provide a short tutorial. Okay, we are almost ready to go. Before we do so, I just wanted to attract your attention on a couple of events that will take place after this one. So we have an upcoming SICAM Marvel Classic lecture in molecular and materials modeling. This will take place on the 20th of May. And we have two rather exceptional speakers in the person of Tony Ladd and Dan Frenkel, who will describe for us their method for computing the free energy of solids and how this relates to a SICAM workshop that took place in 1983. This will start at 3 p.m. on the 20th of May. And if you're curious to have information about this event or previous lectures of this type, please go to the SICAM webpage that you see here at the bottom, and you will find a full menu for you. Following this, on the 3rd of June, we will have the last installment of the Mixed Gen series for this semester. And our speaker is going to be Alessandro Laio. He will talk about estimating the free energy from enhanced sampling to manifold learning. And you can also find information about that lecture and all the lectures in the Mixed Gen series on our website. This is the address. If you scroll down that page, you will find a little tool that will enable you to register for our mailing list. And this is something that I encourage you to do if you are interested in learning or receiving information about our seminars, our webinars, and activities like the Mixed Gen or the classics that we propose from time to time. Okay, this is really all I had to tell you before we get going with our first speaker, Michele Ceriotti, who will discuss for us the thin line between physics and data. Michele, the floor is yours. Thank you.
Thank you very much, Sarah, for the kind introduction and for explaining how this day is gonna work. And thanks everybody for joining us. And before I start with my presentation, I also want to make sure to extend a proper thank you to the members of my group. And here you can see us in our last picture together before COVID forced us to be 1.5 meters apart. And even during the last year, even throughout lockdowns and social distancing laws, they kept working very hard. And as you will see, I have a lot of very recent results that actually were born out of the COVID era. So when Sarah and Ignacio first asked me to give this presentation as this Mixed Gen event, and I realized that I was actually being invited to speak as the experienced researcher. It was one of these midlife crisis moments when you realize that you have way too many gray hairs. And so I decided to start with sort of a recollection of the early days of the field of atomic scale modeling that SECAM is championing to show how the most recent developments in the application of machine learning to this field actually have their roots back in some of the work that went on in the very early days. So if you look at the very first papers that applied computer simulations to the study of materials and molecules at the atomic scale, what you realize very early is that the focus was not so much in obtaining a quantitative description of one specific material, but rather to use very simple models of interatomic potentials, from something as simple as hard spheres to something like Lennard-Jones dispersion interactions or electrostatics. And then the focus was on understanding how the essential nature of these interactions would lead to cooperative emergent behavior when many atoms interacting in these simple ways would be allowed to evolve together, and so giving rise to phase transitions, self-assembly, and so on and so forth. Now, 1 or 2 decades later, advances in computing on one side, but also on the theory of the electronic structure made it possible through density functional theory on one side and a couple clusters on the more quantum chemistry level, made it possible to obtain very precise, accurate predictions of the properties of atoms and the interactions between them without resorting to the use of experiments as a fitting target. And a couple of decades further in the future, with Karp-Marinello molecular dynamics, it really became possible to think of simulating complicated processes at finite temperature, phase transitions, the dynamics of liquids, using a description of the interatomic potential that was first principles and very accurate. However, when you really try to study quantitatively this kind of emergent behavior in matter, you are really up for a very hard challenge, because you need very high levels of accuracy on two different axes, the description of the interatomic potential on one hand, but also the sampling of fluctuations, defects, and all the aspects that go beyond oversimplified description of a molecule as the most stable local minimum of the potential energy surface. And it is really, from this point of view, I believe that the hype surrounding machine learning is largely justified, because, as I will show you, machine learning does deliver techniques that give you the possibility of obtaining accurate predictions of atomic scale properties at the cost that is comparable to that of a classical empirical force field. I want to conclude this sort of overview by acknowledging the fact that many of the ideas that I will discuss today in the context of machine learning models can be traced back to very, very early work that, for instance, considered the study of disordered systems in terms of correlation functions, the study of local order in liquids using order parameters, the prediction, the fitting of potential energy surfaces to first principle reference calculations, using, for instance, cluster expansions for solid state systems and alloys, and fits of potential energy surface of small molecules. So these are all efforts that date back at least 40 or 50 years, and where many of the ideas that I will introduce today can be traced back to. So, getting now on with the machine learning side of my talk, I want to give you a very brief introduction to the problem. This is perhaps unnecessary for many of you, but still, I want to emphasize that when it comes to the application of machine learning to atomistic simulations, you can really identify two different ingredients. One is the machine learning algorithm itself. And here, this is typically a very abstract and generally applicable algorithm that takes a set of inputs and targets that are properties associated with these inputs, and then does something with these. And there are many different possible tasks. So the machine learning algorithm might work by classifying structures that are similar to each other, might work by performing a dimensionality reduction task in which a complex description of a high-dimensional system is automatically distilled into an easier to interpret form. Or, and this will be actually the task I'm mostly focusing on today, you could use machine learning to perform inference, that is, train a model that can then use a new input to predict the properties associated with it. Now, all of these machine learning algorithms are very general, can be applied to any domain. What is special about the application of machine learning to atomistic systems is more the step that goes before this, which is starting from an atomic structure and process it in a representation that can be used as the input of a machine learning model. From the point of view of building these representations, depending on the class of algorithm that you're working with, you might find yourself with different mathematical objects. In the most perhaps simple case, you will be associating a vector of features with individual atomic configurations, but you can also equally well represent atomic structures in terms of distances between pairs of them, or kernels that by and large can be seen as scalar products between feature vectors. Now, a point I want to stress here is that not only it's trivial given a set of features to build a distance between pairs of features, you just take the Euclidean distance between the vectors, or a kernel, you could just take the scalar product, but you can also very often perform the inverse operation and compute features that approximate distances of kernels. So essentially, even if you have different mathematical objects that you can use to represent structures, you can largely consider them to be just different sides of the same coin. talking about regression, which will be the main focus today, the general idea is that you want to be able to predict properties Y of a structure represented with for instance, a set of input features xi, and the way you determine this model function y bar is by minimizing a loss, which is the discrepancy between a set of property values that you have computed for some training structures and the predictions of the model for that same structure. In terms of the complexity of this model, there are many different choices possible. And here, in a very overly simplified manner, I'm sort of sorting different possibilities, going from the simplest linear regression to some kind of deep neural network. And I'm sort of organizing these in terms of the complexity of the function that also underlies its flexibility. And even if this is a very schematic and oversimplified way of portraying the different possible choices for regression, the message that I want to pass here is that not necessarily going towards a more complex model is a universally good idea, because yes, a more complex model will typically give you a better ultimate accuracy, meaning that if you have a sufficient amount of data, you can obtain a better fit of the target function. But usually you will also have higher data requirements. So if you have a small amount of data that you can fit with, which might be the case if you want to use very, very high quality quantum chemistry references, then a simple model, linear regression, or perhaps something intermediate like a kernel regression, might actually be a better choice. At the same time, a deep learning model is more forgiving if you have enough data in terms of a poor choice of representation of your inputs, whereas if you want to use a simple model like linear regression, you really need to have excellent choices of featurizations. I will give you examples of featurizations that are good enough to get linear models with excellent performance. Speaking of regression, another concept that I want to introduce, because I will use it a lot as a diagnostic to investigate and understand the performance of the model, I want to introduce the concept of learning curves. So when you perform this training exercise in which you take some structure, represent them in whatever form you have chosen, train, which means modify the model's parameters to reproduce the structure property relation for the training set. And then the next step is typically to validate your model, assess how accurate it is. And you can do this by setting aside a test set for which you have computed the value of your target properties, but then you also make a prediction using your fitted model. And then you compare the reference value, the predicted value, and you compute the error. And the learning curves are essentially just the process of repeating this training and testing exercise by progressively increasing the size of your training set. And the reason why this is useful is that by analyzing the slope of the learning curves, which is the learning rate, you can understand how efficiently your model can incorporate additional information and improve its performance when it is exposed to a larger training set. So even if I will focus my presentation on this class of supervised learning models that try to predict explicitly the property of your atomistic structures, I also want to spend a couple of slides to say something about unsupervised models. And generally, the idea in unsupervised models is that you only use the structures or an input representation of them to rationalize the irregularities and the patterns that you can find in a complicated system or in a complicated database. So here, for instance, I'm taking a database of carbon structures obtained by ab initio random structure search. So you have a very diverse set of carbon configurations. And what you see here is a two-dimensional map that is built by doing a principal component analysis, a kernel principal component analysis to be precise, based on an input representation of these structures. And what you can see is that you can sort of recognize patterns in which structures of similar dimensionality, for instance, in the case of carbon, gets clustered together, and this can help you understand whether your ab initio random structure search has really covered all the possible configurations or not. And another message that I want to leave in this context is that it might be a good idea, and we are actually trying to experiment with this idea. It might be a good idea to mix unsupervised and supervised tasks. And here you can see how the same map looks like if you build it using kernel principal covariate regression, which is a technique that not only tries to obtain a two-dimensional representation that describes well the structural diversity in your data set, but also tries to make sure that these two-dimensional descriptors are good predictors for a target property, in this case, the cohesive energy of the different structures. And what you can see here is that not only, and this is by construction, this map correlates very well with the energy of the different structures, but you can see also a much better clustering in terms of sp3 diamond-like structures or graphitic structures, different kind of defective graphites, or one-dimensional carbon structures. So you can really see better clustering by including explicitly a supervised target into the procedure. So I was just saying that we are going to now start discussing about representations. So how you map a structure, a molecule or a condensed phase into a representation that is suitable as the input of a machine learning model. And one possible way of seeing why this is very important is just to observe the enormous number of representations that have been proposed over the past couple of decades. And on this sort of phylogenetic tree, we are trying to organize some of these many representations, grouping them together based on similarities in the way they are constructed. And as you can see, starting from Cartesian coordinates, what we try to use as the organizing principle to classify these representations is the sequence of symmetry operations that are used to go from Cartesian coordinate to your ultimate representation. And indeed, the symmetry is one of the main requirements for a representation to be a good representation for atomistic modeling. And perhaps an even more fundamental one is that your representation should be complete, meaning that if you have two structures, they should be mapped to the same vector in feature space, sorry, to different vectors in feature space if you have two distinct structures, because otherwise, of course, since your machine learning model is built based on the feature vector, then these two structures, if they map the same point, will inevitably be predicted with the same properties. At the same time, if instead these two structures are just symmetry-related copies of each other, you don't want them to be mapped to a different point. So a representation should obey basic symmetries: rotational, translational, and permutation invariance. Then you usually want your mapping between structure and features to be smooth and with smooth derivatives, essentially because most of the structure property mappings are smooth. And so if your structure feature mapping is not smooth, your model is basically doomed to have discontinuities. And finally, one requirement, which is perhaps less obvious, is the fact that, particularly if you're interested in learning extensive properties, your mapping should be additive. And what I mean here is that just as the vast majority of empirical models attempt to decompose the energy or the property of your system into a sum of atom-centered contributions, if you require that this is true also for a machine learning model, this has implication for the form of the features or the kernels that you build to describe your structures. So, for instance, if you're trying to use linear models, additivity implies that the feature that you associate with your full structure should be just the sum of features associated with atom-centered environments. If you are building a kernel model, the kernel between structures should be the sum of the kernels between the environments in the two structures. And the reason why you can understand this is a very desirable property is a little bit like in linear scaling electron capture methods. It's a divide and conquer kind of idea. If your model can be decomposed in atom-centered contributions, then a little bit like with Lego bricks, you can train your model on simple structures, then break them apart and put them together into more complex and potentially more interesting configurations. Before I move on to introduce a sort of a construction that allows you to recover the vast majority of the representations that were at the leaves of that phylogenetic tree that I showed you a minute ago, let me also spend 2 minutes to introduce a notation that I will use. And as you will see, we basically borrow the Dirac notation from quantum mechanics. And the idea is that we use Dirac notation for 2 reasons. One, because in the construction of representations, you perform a lot of the linear operations that are so common in quantum mechanics, because quantum mechanics is a linear theory. And second, because Dirac notation emphasizes the fact that the essential ingredients of the theory are independent of the basis you use to practically represent them if you need to actually do calculations with them. And so in this Dirac notation for machine learning, we indicate in the ket the index that labels the structure and some other symbols and indices that essentially indicate the nature of the representation that we're using. And you will understand in which sense I mean the nature in a minute. In the BRA, you can either have a load of indices that refer to the way you actually construct your representation, or just sort of flatten this complicated index structure into a single index, because in the end, when you use your features, you will use them just like a vector of entries, each of which has the same dignity as any other. And when I mean that we use this notation because we do the same operations that you would do in quantum mechanics, you see how in this notation you can change the basis that you're using to represent your structure by doing an integral over the feature indices and using the coefficients that describe the change of basis. If you need to build a kernel, which essentially is a scalar product, well, this is just like a completeness relation in between structure A and structure A prime. And even if you want to build a linear regression model, you can, in a certain sense, regard it as a change of basis, and the coefficients in the linear regression model are just coefficients that are combined with your features to make a prediction using linear regression for the property of your structure. So, how do you use this notation and how do you build a general theory of representations? So the starting point is a Cartesian representation of your structure, which is very simple. Everybody agrees with it, but it's not symmetric. If you just swap the names, the order of these 2 atoms in the listing, it's clearly the same structure, but it's a different vector of numbers. And so your machine learning model would have to learn these permutation invariants. So the first step we perform is representing the structure as a field. And this is basically a density field in this case, which is just a sum of Gaussians or some other localized functions, might be as well direct deltas, centered on the atoms. And we have an additional index that tags the nature of the different atoms. So it's a little bit like each atomic species has a different color. And so you see that with this representation, you can still recognize very well what is the structure, but now the labels that you give to atoms of the same kind are completely irrelevant. So this is permutational invariant, but it's not a translational invariant because this is still dependent on the absolute position in space. So if I rigidly translate my structure, that would be a different function of R cube, and that would be a different vector. So the next step is making the representation translational invariant. And how do we do that? Well, quite simply, we average over the translation group. And the point is that if you do that over the density itself, basically you're just going to end up with a constant because you're integrating a density over R cube. So what we do instead is first build a tensor product of these densities. And if you do that, effectively what you obtain is like a 2-point correlation of this density. And something which is, I think, very, very nice and elegant is that just the act of symmetrizing this density correlation results in a representation of your entire structure that can be written as a sum of atom-centered densities that only depend on distance between atoms, and so it's clearly translational invariant. This is not, however, rotational invariant because this still depends on the absolute orientation in space of your neighbors. So you might have guessed by now, the next step is integrating over rotations. And if you do that...
Before we move to that, Michele, I'm sorry to interrupt, yes, but there is a technical question. Zhedenga He wants to know if the tensor product that you wrote down there is just a mathematical manipulation or if it has a physical meaning.
Well, you could regard this as a mathematical manipulation for sure. I mean, ultimately it is a mathematical manipulation, but as I will show you in a second, the result of this operation is basically that you describe your structure with a hierarchy of n-point correlation functions, which are basically the same endpoint correlation functions you would use in the statistical mechanical description of disordered systems. And so in a certain sense, you could give a physical interpretation to this, even though at this point, it's just a mathematical manipulation to make sure that our representation is invariant. So basically, in a certain sense, answering your question, if you integrate over rotations this atom-centered density, you find something which is basically the pair correlation function, which of course doesn't have a full description of your environment. And so you may want to build, once again, a tensor product of this atom-centered density and integrate the tensor product over rotations, and then you end up with a 3-point correlation function. And you can do this with more and more densities stuck together before you symmetrize. And so you really build a hierarchy of n-point correlations. And something which I also find sort of giving a physical connection to this abstract construction is the fact that if you build a linear model out of these descriptors, the coefficients in the linear model are in spirit and also in practice, pair, free-body, and n-body potentials, which is, of course, an expansion of the energy and many other extensive properties that have been around as a sort of physical concept for a very long time. Now, I mentioned that this construction is kind of a universal construction. And what I mean is that actually starting from these kets, these abstract objects that are built by iteratively tensorizing and symmetrizing the atom density, you can obtain many of the existing representations just by projecting on a suitable basis. So for instance, if you take the translationally symmetrized density and you project it on a basis of plane waves, you end up with something which is essentially the X-ray diffraction spectrum of the structure that has been used as a descriptor to classify crystalline materials. And if you take the rotationally symmetrized endpoint correlation and you project it on appropriate functions, what you obtain is something which is mathematically equivalent to Beller-Parinello symmetry functions that are also used with some slight variations on the theme in the ANI model, in DeepMD, and so on and so forth. So all of these are just a different choice of basis. So it's basically like picking Gaussian type orbitals or Slater type orbitals in quantum chemistry. And then, of course, since we are aiming to do these complicated rotational symmetrizations, a very natural basis to pick is a basis of radial functions and spherical harmonics. And actually, if you do that, this rotational symmetrization that you need to perform to make your representation invariant maps into discrete sums over the indices of the expansion in radial functions and spherical harmonics. And actually, the two-neighbor three-body descriptor is nothing but the SOAP power spectrum that has been used very successfully in this field over the past 10 years or so. And this generalizes easily. I mean, expressions tend to be cumbersome, but there is nothing really conceptually too more difficult than what you need to get SOAP. And you get, for instance, the atomic cluster expansion and many other kinds of representations. So given that there are all of these representations available, and given that I'm telling you that many of these are essentially equivalent, which one should you pick? And one first question that you should ask yourself, which is a fundamental question and hinges on basically what body order of representation you should pick, is, are these representations complete? So are they capable of distinguishing any pair of environments that you might encounter in your material? And actually, this is a highly non-trivial question. So it has been known for quite some time that, for instance, you can build two structures, in this case, two tetrahedra, that have the same list of distances, but they are different. Crucially, these are lists of distances in which we drop the information on between which atom pairs the distances are, but you need to drop this information, otherwise your representation is not permutational invariant. So if you make your representation permutational invariant, you lose injectivity. And at least to me and to many people I know, as a surprise came the fact that also 3 and even 4 body correlation functions and the representations that are built based on them are not injective either. And even though many of the models that have been built this far haven't encountered particular issues due to this, we are convinced that as you aim for higher and higher accuracy, this lack of injectivity will become problematic. So this is a fundamental issue, but now how about choosing between two representations that have the same body order, so they are morally the same? Can you quantify whether one choice of basis is better than another? And from this point of view, we have recently proposed this feature space reconstruction error, which is a very simple measure of the, loosely speaking, information content that allows you to compare two representations. So the idea here is super simple. So you have the same data represented with two representations, and you try to use features f to linearly predict features f prime. And you measure the minimum error that you can make approximating features f prime using f as inputs. Now, this representation is obviously not symmetric, so it might be, for instance, easy to approximate f prime using f as inputs, but not easy to approximate f using f prime as input. This would imply that f contains more information than f prime, because it's simple to approximate f prime given f, but not vice versa. And for instance, if you try and converge by increasing the number of features a SOAP or a Beller-Parinello symmetry function description of two different data sets, what you see is that as you increase the number of features, the error in approximating atom-centered symmetry functions using SOAP decreases, and in this case goes towards 0, but not vice versa. And this is just a reflection of the fact that SOAP uses an orthogonal systematically convergent basis, and the usual Beller-Parinello symmetry functions are not orthogonal systematically convergent basis. So just in terms of information content, you can objectively say that SOAP features are better than Beller Parinello features. However, of course, the story is more complicated than that because features and models go hand in hand. And for instance, if you use empirically, models based on Beller Parinello symmetry functions have usually come up with comparable accuracy when using a neural network model as SOAP models based on kernel ridge regression. So the different things are coupled, and this is still largely an open problem. And I find kind of interesting, this is for the venerable QM9 dataset, I find kind of interesting to see how with very similar accuracies, you get models that use kernels, models that use linear regression, and models that use more or less deep neural networks. So really, models and features are bundled together, and it's not so easy to disentangle them. And one last consideration is that you should have very clearly in mind what you want to achieve by using a certain set of features. And here I'm giving you an example of analyzing the solidification of a multi-million atom box of molten iron. And on the left, I'm analyzing these based on the kernel principal component analysis built on SOAP features, so rotational invariant. And on the right, I'm using instead features that are not rotational invariant, basically just the density expansion coefficients. And what you can see is that as you start nucleating the solid phase, well, in the invariant case, all the grains have the same color because the descriptors are rotational invariant. In the rotational invariant case, instead, different grains have different color because they have a different orientation. So if you wanted, for instance, to analyze the texture of this sample, it would be much better to use descriptors that are not rotational invariant. So, you need to know what you want in order not to lose the information that you may need. Another reason why you may want not to have rotational invariance is if you need to learn a property that is not invariant, that is not a scalar. So, for instance, if you want to build a model for something like a dipole moment, well, then the question is, how does your model change when you rotate your structure? So what is the dipole of a structure that is rotated when it's predicted by your model? And here you see that I'm using a representation in which I'm adding an index in the ket. And this index is important because this index will describe the rotational properties of this descriptor. So now these features are not only indexed by the feature vector, but they are actually also indexed by a second index that has to do with the rotational properties. So if you can build features that transform under rotation, like the application of a rotation matrix with respect to this geometric index, then your model will automatically and naturally rotate together with your molecule, which is what you want. You want your model to be covariant with respect to rotations. And actually it turns out that within this same general endpoint density correlation framework, you can also build features that obey these rotational properties. And actually they obey a generalization of the rotational properties of a vector that is basically the rotational properties of spherical harmonics that are described by Wigner matrices. And the way to build these is essentially to put inside your tensor product that you're symmetrizing also a spherical harmonic that keeps track of the reference system. And using these symmetry adapted models, you can, for instance, build a machine learning scheme to predict the polarizability, which is a tensor, and therefore needs to be predicted with its full anisotropic behavior. And you can do this very naturally using this formalism. And you can come up with a model which actually beats DFT at making predictions for molecules that are much larger than those the model has been trained on. So here you really see the advantage of locality. We can run thousands of couple cluster calculations with small molecules and then make predictions for molecules that are much larger. And if you want to get even more esoteric, you can also build models for the electron density once you realize that a practical way of describing the electron density of an extended system is by breaking it down into contributions that are atom-centered. And you have resolution of the identity basis to do this. And the coefficients in this local expansion of the density transform like spherical harmonics, and therefore need this kind of symmetry-adapted machine learning scheme to be learned effectively. And then you get a model that is very transferable, again, thanks to the locality. Now, another reason for having symmetry-adapted features is that you can use them to build in a very natural, I will not say it's simple because there are a load of indices, as you can see from, from how many colors I had to use. But the idea is actually relatively easy to understand. So the idea is that if you have features that transform like angular momenta, then you can combine them and obtain features that transform like angular momenta just by using the formula for summing two angular momenta. So these are Klebsch-Korman coefficients, and this is a systematic recursive iteration to build equivariant features of higher order by combining equivariant features of lower order. And this actually can also be used to compute efficiently invariant features, because invariant features are just equivariants with lambda equal 0. Now, one of the problems, if you want to apply this idea in practice, is that the number of these features, even though you can compute each of them efficiently, the number of these grows exponentially with the body order. And the idea we came up with, which we call the n-body iterative contraction of equivariance, is that you should couple this body order operation, this iteration that explodes the number of features that you have, with a contraction or a subselection that only picks the most relevant of these features before you proceed to the next level of iteration. So, and then this basically allows you to build models that can be systematically improved by increasing the body order. And here you can see how this gets better and better as we add more terms in the expansion. Now, all the models up to this point have been based on this local approximation. And the question, of course, is how far can we push this? And you might think, okay, this is just a convergence parameter. I increase the cutoff. The larger the cutoff, the better my model will be. And actually, the reality is a little bit more complicated than that. And if you build different models, and again, here I'm coming back to this QM9 data set. So these are molecular atomization energies that we're trying to predict. And perhaps surprisingly, a very short range cutoff of 2 angstrom, if you have a small data set, gives you a better accuracy than a long range cutoff. And the reason is that this is a simpler model with fewer with a smaller complexity. Even if you use very many features, the inherent complexity of the model is low, and still is pretty good at picking up covalent bonds that make up a large fraction of the cohesive energy of molecules. However, if you have a lot of data, then this model saturates because it can't describe hydrogen bonds or all other sorts of longer range physics. So you can sort of put this intuition that physics is multi-scale, which is perhaps not so surprising, into the model by building multi-scale models that combine different length scales with an appropriate weighting. But the problem is that if you then think about something like electrostatics, then it's very hard to imagine this kind of scheme to be effective. And you can see one way of seeing why is that if you look at the cohesive energy of an ionic solid that is entirely dominated by electrostatics, it's a well-known fact that you would get a different answer for what is the cohesive energy if you try to converge its calculation by summing over spheres or summing over tubes. So you can imagine how hard it would be to brute force converge a machine learning model for something which is dominated by electrostatics. And indeed, if you look, for instance, at the binding curve of charged dimers, you will see that the local model saturates, and whereas the real binding curve still changes on the scale of the, tenths of a Hartree, 50 angstrom away from the origin.
Sorry, let me interrupt you because we have a question from Sergio De Checchi, who would like to know if you expect that a small radius is effectively regularizing the solution.
Then I think so. Yes, in many ways, yes. It's making sure that you don't overfit your model. Yes, that's one way of seeing it, and this is also why when we put the long-range information in, but with a very small weight, we still perform well in the low data regime. So, and yes.
Does this procedure affect the condition of the kernel matrix?
The multi-scale construction, we never checked, but I would expect it does, because typically the multi-scale kernel matrix is dominated by like a factor of 1,000 by the short-range kernel. So, and the short-range kernel tends to be better conditioned, yes.
The regularization, huh? Yeah. Mm-hmm.
Yes. One of the problems, if you want to deal with genuinely long-range behavior, is that you want sort of to put together the divide and conquer nature of local models and the capability of capturing this kind of long-range physics that is very hard to converge by brute force. So our solution here to sort of getting the cake and eating it too was to proceed as follows. So we start from the global description of the structure using an atom-centered density, and we solve the Poisson equation for it. We compute the potential which is associated with this density. Now, this is not a physical potential. We have a different potential for each chemical species. So this is just an abstract potential associated with the density. But it can be computed efficiently in reciprocal space, much as you would do for the real potential. And then we basically do the same gig. We symmetrize, we decompose, and then we have local expansions of this potential, which are the features that we use for learning. So in a certain sense, we have something which has global information, but compressed into a local environment. And also this scheme, you can sort of bring into this general universal construction of representations, because the only thing that you're doing is that you are throwing inside this hard integral that gives you this symmetrization over rotations, some of these fields that you have computed by a global step. And turns out that if you do this, you end up with a representation that works very well at describing the asymptotic behavior of interactions. And you can actually also show analytically that a linear model would correspond to a multiple expansion. So there is also some physics that goes into this. And indeed, the charged interactions come out beautifully. But what is kind of remarkable is that even for interactions that are most definitely not dominated by electrostatics, you get very good extrapolative behavior. And what really genuinely surprised me was that we could get very good fits even for something like the interaction of a molecule with a metallic surface, which is an extremely polarizable scenario in which you would expect that something that is at least loosely speaking inspired by point electrostatics wouldn't work very well. So up to this point, I have given you a sort of very formal introduction to the problem of machine learning, but I want to briefly, I don't know, Sarah, if you can get a couple extra minutes given the questions and the blackout.
Of course.
So I want to give you a few examples of how, in my opinion, this is already changing the way we can do atomistic simulations. And I want to start with something which has been something in which the community has devoted a tremendous effort. So the calculation of thermodynamics at finite temperatures from first principles. Now, this used to be an extremely difficult game that requires very, very careful, ladder of DFT of increasingly high accuracy. So this was a very, very difficult kind of, milestone calculations have been made to get the finite temperature thermodynamics of materials. Now, using machine learning as a stepping stone, this is relatively easy. I mean, it's not really easy, but it's something which you can do to very different systems. You can compute the melting point of water, the relative stability of hexagonal and cubic ice, which requires an incredibly high level of accuracy. You can compute the properties of matter in extreme conditions. You can compute phase diagrams of binary systems, and here I'm showing gallium arsenide. This is a very complicated system for an empirical potential, because you have, through the phase diagram, you have an ionic semiconductor and a molten metal, a molecular metal for pure gallium, and you can build a machine learning model that encompasses all of these and is cheap enough that you can run a long simulation with a big box and build a phase diagram. And I think that the error with respect to experiment here is due more to the ab initio reference than to the machine learning model. Now, at the same time, machine learning is not perfect. So, for instance, for water, we had to do free energy perturbation because of the lack of electrostatic interactions. All of these fancy long-distance equivariants are very promising, but we don't have yet an implementation that we can apply to large-scale problems. So, for the moment, we go pragmatic and we do free energy perturbation, which works very well. And another aspect in which you might still need to go back to first principle calculations is when you want to compute properties that are not easily fitted by machine learning. So here, for instance, we needed the spin density, didn't have a machine learning model for it, had to run more calculations to get it after having run the molecular dynamics simulations using a machine learning potential. So one direction in which I think the field is moving and should move is in the construction of what I call integrated machine learning models that combine all the properties that you could hope to get from a quantum mechanical calculation. And so here, for instance, we are computing the IR and Raman spectra of liquid water, and everything from the potential to the dipole moments to the polarizabilities are computed with a machine learning model. Another example here, we can compute the electron density of states, and we can use the electron density of states to compute the electronic contribution to the heat capacity for metals at high temperature. And this works super well. So just with machine learning, without having to do additional DFT calculations, you can also get electronic properties. And all can be brought together, and this is a very nice paper to which we actually contributed at the very last minute. This is really Volker Deringer's work, they had fantastic simulations of silicon, amorphous silicon undergoing phase transition at high pressure, and we could add density of states for the electronic structure computed at the high level of density functional theory, and compute them for boxes that contain the 100,000 atoms. So this is really one direction in which I can see the field moving. Another aspect which I think is very promising is using machine learning as an analytics tool. And the idea here is what I call knockout machine learning models. So the idea is that you play around with different machine learning models for the structure property relationship that you're trying to understand. And by using machine learning models like the one that I discussed today, in which you can understand what are the different ingredients, you can see, for instance, how much three-point correlations matter, how much long-range contributions matter in determining your structure property relationship. And last but not least, nothing of this would be possible without an efficient and well-designed software stack. And here, really, I mean, again, it's worth to spend a second to thank the members of my group who have been spending a lot of, thankless work into making sure that all of these software components work well, reliably, can interoperate with each other, and can also interoperate with the other tools that are developed either in my group or in the broader community. So this is a very important part of the work going forward. So to sort of wrap up and get on to my conclusions, the thin line between physics and data that was in my title is not only thin, but is also, in my opinion, increasingly porous. And you can really observe concepts from the physical world percolate into the machine learning realm. And this goes from symmetries, the exploitation of locality, trying to incorporate scaling laws, conservation laws, descriptors that capture the right asymptotic behavior by construction. And, if not for anything else, the targets for our models still come from physics-based modeling. So I think that, in no way electronic structure theory, DFT, and higher accuracy methods are going to go away. They are just going to serve a different purpose and be integrated together with the machine learning techniques. And here, for instance, I should say, for instance, that Georg Kresse has implemented in VASP machine learning schemes that are already functioning together with one of the most widely used commercial codes for DFT. And I think that this is great, that this is one of the directions in which the field is moving and should move. And also on the other front, data is starting to contaminate the way of doing physics, and this at the simplest level comes from having affordable accuracy so that you can do more physics with the accuracy of high-end electronic structural theory. From the point of view of building, of model-based physics, you can now add some terms that allow you to complement your empirical models to go beyond the accuracy that you can achieve with them. And also, I'm really convinced that the advanced analytics that allows you to analyze large amount of data and to play with the with understanding in which way a machine learning model works or not is also something that can help us understand physics. And the combination of the two is, in my opinion, really going in the direction of having these integrated machine learning models that substitute, I shouldn't say substitute, but provide a surrogate model for any property that you can compute with quantum calculations, and in this way extend dramatically the mileage that you can extract from a small number of quantum calculations. I think that there is a lot to gain from developing what I call multi-paradigm simulations. So the idea is that, for instance, you predict the density of states using machine learning, but then you use just a simple physical model to compute the electronic heat capacity from the knowledge of the density of states. This is just a very simple example, but you don't directly predict the electronic heat capacity. You go through the electronic density of states, which is in many ways a better target for learning. And the last point and the last thing that I want to say is that I believe that this combination of machine learning and physics is really going to sort of realize this program that started in the 50s with the modeling of complex collective behavior and emergent phenomena, and is going to make it possible to routinely model this kind of complicated collective physics with an accuracy which is quantitative and predictive. So thank you for your attention. And if you have any more questions, I think we have still a few minutes.
Well, we will certainly find a few minutes for the questions that are already typed in the Q&A. I would like to remind the people who have typed questions that this is the time to ask them live. So in a couple of seconds, we're going to invite you to unmute. We're going to just proceed in chronological order for these questions. But before we do that, Michele, thank you very much for this interesting and brave talk. I mean, I do think that it takes an experienced speaker to, survive a blackout, internet connections with problems, and still show off a fairly black beard from what I can see here.
Yes.
So, okay, that's
light.
Light
came back up.
So, okay, let's start with the question. Rangsiman, you are on first.
Yes, thank you, Michael, for your wonderful talk. I do have a question about the SOAP descriptor. For usually in the SOAP descriptor, it makes use the combination between the spherical harmonics and the radial basis function, right? But when we use it in practical, for example, if I set the angular momentum or the L parameter to 0, this will remove the coupling between the spherical harmonics and the radial basis function. So how can we deal with how can we solve this problem? For example, how can we apply the superposition between these two things in the SOAP?
I'm not sure that I understand. You're asking what happens if you set the maximum L channel to 0?
Yes, exactly. For example, I set it to 0.
Well, if you set it to 0, I mean, you are doing an expansion, right? So if you want to have a full description of the ket within the basis, you need to converge the basis. So the sort of dismissive answer would be if you set L max to 0, you just haven't converged your basis. The slightly less dismissive answer is that you then get something which is related to the two-body descriptor. It's basically just the square of the two-body descriptor. So you effectively have a two-body descriptor at that point.
Yeah, and just a small question. So what is the optimal value of the L parameter? Like, what should I set it to be?
So this is a more subtle question than you might expect. So in general, there is, so you might also, so this is a little complicated in the sense that what you're trying to do is approximate a function, and this function will have a natural degree of smoothness, okay, a natural degree of regularity. And what you want is that your, in order to be that efficient effectively, you want your representation to be as sufficiently flexible in combination with your model to represent the smoothness of your function, but not more and not less. So the smoothness of your Gaussians, the smoothness, the number of L channels, which basically relates to how sharp can the changes in your representation be, and the regularization in the regression problem are all bound together, in my opinion, quite inextricably. And so in practice, this is a parameter that you may want to converge and, well, which you might want to optimize. But in general, there aren't massive changes in performance if you over-converge it. But it's a little more subtle than what one might expect.
I see. Thank you very much.
Okay, we are ready to move to Yubo Yang.
Oh, hello. I was just curious. In one of the last slides you showed that the heat capacity predicted by the neural network does not capture the peak in the experiment. I was just wondering why that's the case.
Yeah, that's an excellent question, but it's an easy answer. This is nickel. It's magnetic, and it has a Curie temperature of 600 something Kelvin. So this is the magnetic peak. And we are not describing magnetism in the model right now. So it's just physics that we are not capturing. And for nickel, it's okay because it's a soft ferromagnet, and we are particularly interested in the high temperature regime. And so we don't really need magnetism. But of course, incorporating magnetism is one possibly interesting way to, to continue this program of mixing up physical models and machine learning.
Gotcha, thank you.
Giancarlo Francese.
Yes, thank you, Michele, for this nice talk. You presented the case of water, no, for your examples, and I'm curious to know, and also the effect of temperature. Can you estimate the two-body, three-body, and n-body contribution to the interaction, including, of course, the quantum effect as a function of temperature in the case of water?
Oh, okay, not with this model. This is a, let me see, yes. This is based on a Beller-Parinello neural network. And so, strictly speaking, all of the body order terms are bundled together, and I don't think you can disentangle them easily. It would be interesting to build a model in which you can separate out the different body order terms and try to see how they play with each other, but this is not something that you can do with this model.
Okay, thank you for the pity.
Zeng Dahe.
Okay, thank you, Professor Charotti, for your really nice talk. I want to ask, so is there any studies by using SOAP as the feature for neural network, and how does that compare with the kernel ridge regression that you have been using?
That's an excellent question, and to be honest, I'm not sure. I'm not aware of any, but I don't see why not. My expectation would be that probably it wouldn't probably help too much, because when I show you something like this, what is missing in this kind of picture is the correlation between the features and the target properties. Okay, so here I'm just really trying to measure the absolute information content of the features. This is an unsupervised exercise, if you wish. And in practice, and if Jorg or Gabor are listening, they can chime in. My understanding is that Beller-Parinello symmetry functions are so successful because the functional form they use, even though it's not orthogonal, it's not systematically convergent, it has a lot of objectively problematic mathematical properties, is actually very well suited to describe the typical target, which is a potential. Okay, a typical example that I will make, because I think it's really nice, and it's a big testament to the insight of Jorg, Michele, and all their collaborators. So in this multi-scale kernel model, you can achieve a very similar effect to this combination of different length scales by introducing a scaling function that decreases the importance of density contributions from the far field in the construction of your SOAP vectors. Okay. Mm-hmm. And if you go and look at the radial cutoff that is used in the typical implementations of Beller-Parinello neural networks, you will see that it's a very strange cutoff. Usually cutoffs start 0.5 angstrom from the cutoff and they go down very sharply. Instead, the cutoff function that is used is very smooth and starts already cutting off close to zero. And I think that, this, in retrospect, this makes a lot of sense because it incorporates the notion that the far field will be less important in determining the meat of the interatomic potential. So I do realize that I spoke a lot without really answering your question. I'm not sure that SOAP has ever been used. I'm not sure it would, be massively better than Beller-Parinello symmetry functions because of these.
Okay. Thank you so much. Yeah.
Okay, thank you. We have a few more questions and we are running late, but I think, this is CCAM, so we're not going to really bother about time too much for the time being. But if it gets really, really bad, I will ask you to ask some of these questions offline or maybe in the gathered time. So Eric van den Enden.
Yes, hi, Michele. Thank you very much for this beautiful talk.
Thanks.
So I have a question which is maybe like an old gen question, which is and it's a bit of a generic question, which is that all of these beautiful results that you show that rely on machine learning, in some sense rely on the approximation power, like of neural network, right? And on the ability to beat the curse of dimensionality that plague other approximation, more classical approximation representation. So I'd like to have your take a bit on this, which is, is there any way we can actually really benchmark this and really, assess the accuracy of these results? How, and maybe also, is there a way through this calculation, through molecular dynamics, to actually understand why neural networks are doing so well? I understand it's a very generic question, but I mean, since you are there and you're doing so many things on, with this, I'd like to have your take on it.
So, okay, I have, so I don't know if you would agree with this oversimplified scheme that I drew at the beginning, but in my experience, it's actually not so obvious that neural networks would do better than a kernel model or even a linear regression model if it's built on good features. And I can substantiate this statement with two plots. One is this so one is this one, okay, where basically for relatively if in the end, if you care about getting to 0.5 kilocalorie per mole on this specific problem, okay, lots of caveats, but the best models are kernel models, and a close second is linear regression. This nice model is linear regression. And also here, this is a very different data set. This is a database of, in total, we have 1 million random configurations of CH4. And what you can see here is that, yes, in the end, it's very hard to get a linear model that has the same flexibility as a neural network. And you know this much better than I, of course. The complexity per parameter that you get out of a neural network is much, much higher. But if you have a limited amount of data, and I mean, 10,000 structures are not a small number if all that you're trying to approximate is CH4, a linear model can beat the crap out of a neural network. So I think that the story is a little bit more complicated.
Okay, thank you very much.
Oops, thank you both. Let's move to Shankana.
Hello, can you hear me? No.
Yes.
Okay. First, I want to thank Professor Chayoti for giving this wonderful overview. So I have two questions. One is that, like, for example, in a high entropy alloy, for example, like I arrange different atomic species on a lattice of a certain size, and then I calculate the relaxed energy, and I say that, okay, this arrangement gives this energy, but it is not the real energy, but the relaxed energy. Or I can also use the free energy. And if I have a lot of these like arrangements versus energy, and I have this data and I give it to the neural network, will it be able to give me the free energy or the relaxed energy of a new arrangement? So that is one question. And the second question is that you have shown the linear expansion with the bond with the different bond orders, like the distance and the angles and stuff like that. So if I go to really high bond orders, like really high bond orders, then is it possible? Can I think of it like if I just have 2 data points, I can basically get all the coefficients exactly fitting my my energy. That means my question is like whether it is really a linear approximation or it is non-linear thing, which we are kind of approximating with a linear expansion. So that is my two questions.
Okay, so the second question first. If you go sufficiently high in body order, you get a complete basis to linearly expand your properties.
Yes.
Now, whether this is achievable in practice is another story, because of course you also need a complete convergence of the basis of the density, and because the number of—
Can you repeat? My net actually cut me off. Sorry, I'm very sorry. Can you repeat the last line, please?
Yes, so you need to converge the density expansion, and you need to cope with the fact that the number of terms in the new body correlation increase exponentially with nu. So in principle, you can get a complete basis. Whether you can get there is another story. There are very good, promising results from ACE, from NTP, which are built on the notion that you can converge a linear expansion. So there is a lot of promising action in this direction, but it is an approximation problem.
Okay, so approximation.
And your first question is actually a more complicated one, and I will try to see if I can write. Do you see my writing?
Not yet.
You don't see lines appearing on the screen?
No.
Oh, okay, then I can't write, sorry. But basically, the problem that you have is that is a conceptual problem. So if you want to compute the free energy of a configuration, that's not a function of an individual configuration. That's a function of an ensemble of configurations.
Yes, it's an integration.
So you need to formulate your problem appropriately. So actually, we discuss a little bit these in this review as one of the potential issues going forward. So you need, and one possibility is to say, okay, if I only have small fluctuations around a structure, then I could use the idealized geometry as a proxy for the ensemble. So that might be a way to give some solid foundations to this question of computing the free energy of a given configuration.
Okay, and the relaxed energy also, we will say the same thing, but that is the relaxed energy is not integration.
I would say so. So something that we have done is, again, on this QM9. You know, QM9 gets a lot of bad press, but it has been a fantastic tool, and I think it has really pushed the community forward a lot. So the QM9, the typical QM9 benchmark, is completely useless, right? Because what you do is you take the geometries that are optimized by DFT, and you use them as the input to predict the DFT energy. Okay, so it's a very similar situation. It's if you have to relax to DFT level to get the input to predict the DFT energy, that's a very academic exercise.
Exactly.
Right? So something that we have tried to do and works pretty well is that you optimize the geometry at a semi-empirical level of theory, and you use that to make a prediction of the DFT energy at the optimized geometry. So this is pretty much the same thing as what you are trying to do. So I think that, yes, it works much less well, of course, than if you have the optimized geometry as input, but is then a much more useful exercise, and so it's worth doing it.
Okay, thank you very much for your responses. Thank you very much.
Okay, let's take at least another question. Ganesh Silvaraman.
Hi, this is Ganesh Silvaraman from Argonne National Lab. So I was wondering about the phase diagram. I think it's related to the gallium arsenide. So was that computed with the neural network?
Yes, this is computed from a neural network.
And coexistence simulation or all these?
So in practice, this is done with coexistence simulations, yes. And it's actually pretty neat. Honestly, we haven't been able to find these in the literature. I'm sure it has been done already, but it's sort of cute. So the way we do this is that we do Monte Carlo exchanges at constant total number of particles. And the result of this is that the difference in chemical potential between you basically end up with a pinning potential that is coming from the difference in composition between the two phases. And so you run this simulation, and then you can compute the slope, and you get the free energy of the liquidus and the solidus, and you can build the phase diagram this way.
That is very interesting. So does that mean that you would have to encode all those interfaces into the training data?
So yes, but you actually, I mean, the most difficult part here was more actually to avoid weird things happen in the bulk. The big problems that we had were like completely absurd. You know, we really had to converge all the anti-site energies because otherwise it would start clustering some weird arsenic inclusions in the bulk. So the interface, we just needed a few tens of configurations. It wasn't so bad.
Yeah, that is very interesting. That's what I was also thinking in terms of like, what if it ends up in some unrealistic configuration and then it gets stuck.
So one thing that helps a lot in this respect, and you know, I like all these very formal things, but in the end, one has to be pragmatic. And so what we are doing more and more when we have difficult problems like this one is to use online uncertainty estimation. So basically, we run the model with built-in uncertainty, and we just do what we want to do. And then we stop and update the model every time we get too large uncertainties. And many people are doing the same because, of course, this is a very practical approach. You start doing your thing, and you keep adding data to the training set only until you need to.
Right, and I'm assuming that it's uncertainty in the forces.
Yeah, no, it's uncertainty in the energy and the forces, yes.
Okay, I'm sorry to interrupt.
Thank you so much. Yeah.
Okay, thank you, Gane. Michele, I have a question for you. Will you be with us also for the Gather poster session?
Yes, I will.
So then what I would suggest is that we take one more question live, and I would ask those who, Luca Grisanti, Alessandro Laio, and then Sergio again, to maybe take their questions during the poster session on Gather. So we have Kateresa Azizi, I apologize for the pronunciation.
Yes, thank you very much for the very nice talk. I have a very simple question. So regarding the symmetries that we are applying on the method, is the methods and the representations only limited to the symmetrical systems? And so, for example, if we have a molecule beside the surface, can we also look at the properties of that molecule? Because I saw some water molecule near a surface that the dipoles were studying.
So you shouldn't interpret these symmetries as crystal symmetries or point group symmetries. These are really rigid rotations of the entire system. So even a molecule on a surface, if you rotate rigidly the molecule and the surface, you should get the same energy. So these are the only types of symmetries that we are applying. So there is no problem whatsoever in modeling a liquid, a surface, a molecule that is exploding. There are no discrete symmetries that are enforced, except for inversion, because inversion is a symmetry that also applies at least.
Thank you very much. Thanks.
Okay, thank you, everybody, for asking these really interesting questions and for having some discussion. I mean, it's not easy when you are not in the same room, but I think we managed to have some meaningful exchanges. And I apologize to Luca, Alessandro, and Sergio, but please come to the Gather Town session and
I'll be there with a beer.
And hunt Michele down so you can keep asking questions. If you don't have the link, just send me a note and I will make sure that you do. And now I think it's time to move to the second speaker for this webinar, David Peter Kovacs from Cambridge University. So David, the floor is yours.
Okay. Let's see if you see my screen first. Right, okay. So can you see my screen and can you see me?
Perfect.
Okay, very good. Okay, so hello, I'm David. So I'm a first year PhD student in the group of Professor Gabor Csányi in Cambridge. And so I'd like to talk to you about atomic cluster expansion force fields for organic molecules. And so I'm very lucky to have Michele talk before me because he has introduced so many of the concepts that I will also talk about. And so he was referring to atomic cluster expansion as ACE. And I'll do so as well. So ACE is what he was also talking about. So I will tell you how we can take this framework and build force fields for simulating organic molecules. So first I'll just sort of quickly motivate why we are building organic force fields. And then I will introduce atomic cluster expansion, which is sort of a concrete example of these symmetrized density field kind of expansions. And then I will actually show some results as well on small and larger molecules, tell you why we think this atomic cluster expansion and linear regression is hopefully the best way forward, or a very good way at least. And then I will give some summary and maybe a bit of an outlook. So to sort of set the field first, so I'm traditionally in molecular simulations of organic and molecular materials, the approach has been molecular mechanics, and in the past 10 years it's been machine learning. And so here I am in this table, I'm a bit contrasting the two methods. So molecular mechanics basically builds on physics-inspired functional form. So it means that there are these kind of bond terms and then angle terms and also sort of dihedral terms. And this is really what goes into the model. And most of them are sort of harmonic approximations or something similar. And so if you can think of these as a body order expansion. So you have this bond is like a 2-body effect, angle is a 3-body, and then dihedral is a 4-body. So what is kind of annoying with these models is that they have a fixed topology, and it's also kind of limiting because basically when you start a simulation, you have to specify which atoms are bonded together. And this means that your force field by design cannot be reactive. So you just say that, for example, this is a bond, and then it has a certain harmonic bond constant, and then that's it. It's not allowed to change during the simulation. What is good, though, is that these models have relatively few parameters, and the philosophy of actually obtaining the parameters is that they are usually fitted first to quantum mechanical data, and then the parameters are refined so that some important properties of the system, such as density or viscosity, are reproduced at the experimental level. So basically, the parameterization is a mixture of sort of bottom-up quantum mechanics and top-down empirical modeling. So on the other hand is machine learning. So here I have sort of said a few examples are ANI or Gaussian approximation potentials, and more recently NEQUIP and other equivariant graph neural networks. So they take a very different approach compared to molecular mechanics, and they start with a very flexible functional form, be it a neural network, a feed-forward neural network, or a kernel, or a graph neural network. And they basically try to think about the energy as being made up of atom-centered or atomic side energy contributions. So they don't have this body order expansion of the energy. And these models are usually topology free, and they have a very large number of parameters, which is kind of the same as saying that they are very flexible. And usually they are fitted purely to quantum mechanical data. So what I'd like to convince you about is that atomic cluster expansion is somewhere in between these two, and it has best of both worlds as well. So when we want to derive atomic cluster expansion, we really start with a body order expansion. So we want to write the site energy, so that's kind of machine learning, but we write the site energy in terms of body ordered terms. So we have basically this is a one body term, and then we have two body, three body. So this is sort of two, one neighbor or two neighbor, etc. And then what I need to introduce is something that we call the one bond basis functions. So this is something extremely similar to, for example, SOAP. So in SOAP descriptor, you also have a radial basis and you have an angular sort of spherical harmonic. And then we consider the atomic neighborhood density, which is in this case slightly different from SOAP because we write it in terms of delta functions. So basically we are sitting at a central atom and then we take a cutoff, and within a cutoff radius, we put a delta function at the position of all of our neighbors. And then that is what we call, the sum of this is what we call the atomic neighborhood density. And then what we do is that we sort of project this atomic neighborhood density on our one bond basis set that we defined before, which is a radial and an angular basis function. And this way we arrive at these A functions. So then this projection ends up just being a sum over the neighbors, and we evaluate these one bond basis functions on the position of the neighbors from the central atom. And then we can expand the site energy in terms of this A, which we call the atomic base. So what do we get? So we get basically these two body terms, which is just the site basis functions evaluated at the neighbors. And then we have, it for each neighbor. And then if you take products of these, then we get effectively three body contributions, because the product of, for example, these two is something like this. The product of some other, like this two, will be something like this. So effectively, we can very efficiently get three body contribution by a single product. So we don't have to sum over all triplets or sum over all quadruplets in our system, but we can just take products of these simple expansions of the neighborhood density, and this way we can efficiently get arbitrary high order correlations in the system. And then we have these linear expansion coefficients. And there is one thing that I haven't told you about is how we make this whole thing rotationally invariant. And that's sort of conceptually quite simple because we just need to use the C, which is the Clebsch-Gordon coefficients, and using them we can kind of, this is a sparse matrix which takes the combinations of these atomic basis functions that are going to be rotationally invariant, or if you want to build an equivariant basis set, then we can just use a different set of Clebsch-Gordon-like coefficients, and we can also build an equivariant basis set. So our final expansion for the energy is just a linear combination of these basis functions. So basis functions are features, you can use them interchangeably. So here we call them basis functions. So basically we just write the energy as a linear sum over these symmetric, rotationally, permutationally, translationally invariant basis functions. And then the fitting of an ace potential is sort of quite straightforward. We basically just do a linear least squares fit, and then we apply some regularization. So here it's like a ridge regression type regularization. And then there is a number of linear algebra solvers like LSQR or RRQR, which are quite robust and can be used if the system is not too big. If it's too big, then we might have to go to gradient-based optimization. But for most cases and for sort of small molecular force fields, usually we can get away with the very robust linear algebra solvers that don't need gradient-based optimization. So the first question that arises is that how accurate is this method? Because it's still just linear regression, and then we sort of decided to compare it to the other methods out there. So what you can see here is a table of accuracies on 10 different small organic molecules. So they rise from like aspirin or malonidahide or paracetamol. And so here I have some mean absolute errors in milliev. So you can see that these are well below 1 kcal per mole, which would be like 43 milliev. So this is really very accurate models that we are talking about. And so the comparison is made between so SGDML and GAP, which are two kernel models, ANI, which is a neural network model, SHA is another kernel model, sorry, and then the FF here is the classical molecular mechanics force field, which we have also parameterized for these molecules. And so what you can see from this table is that our linear regression-based atomic cluster expansion model is able to achieve the highest accuracy across all of these molecules. And then there are also a number of other models in the literature, which are, these two are equivariant neural network, and this is a graph neural network. And then, so these models can also achieve really quite low errors overall. But it's quite interesting that even though, for example, this pain model is as accurate as ACE on forces, the energy accuracy of pain is actually 3 times worse. So we think it's quite important, because even though the short sort of trajectory of a molecular dynamics simulation that you might want to do with these molecules is only determined by force accuracy, but on the long run, so if you run a very long simulation, then the energy accuracy will be what actually determines the sort of Boltzmann weight of the different states of the molecule. So we think that it's really important to be accurate on both energies and forces. So then we looked at a few other things. So what we can do with these models. So we can, for example, calculate vibrational frequencies of the normal modes. So you can see here, for example, for toluene, and we compare them against the DFT quantum mechanical results. And what's interesting is that, for example, in the case of toluene, so F here refers to the force error from the table in the previous slide, and the nu here refers to the frequency error. And you can see that it can happen, and it does actually, that a model that is more accurate on forces and energies is actually less accurate in predicting normal mode frequencies. And what's quite interesting is that we have parameterized a few models, so all of these, and what we find is that ACE is actually able to achieve the most accurate vibrational frequencies by quite a large margin. And this is in some sense extrapolation task, because the relaxed geometries were not part of the training set. So the training set was made up of 500 Kelvin molecular dynamics configurations. And you can see that ACE is actually really very accurately capturing the sort of geometry of the potential energy surface around the minima. So what is also nice is that the atomic cluster expansion gives you a lot of freedom, because in the body order expansion, you can decide to truncate it anywhere you like. For example, go to 3-body, 4-body, 5-body, and you can also decide how much degree of freedom you afford at each body order. So you can say that I want to take a degree 15 polynomials for 2-body, degree 15 for 3-body, but only degree 12 for a 5-body, and this way you can really tune the speed of your model. So you know, if I want more speed, then I can just decrease the basis set, and you can see I lose some accuracy. But as you can see, if in both the case of ethanol and azobenzene, the atomic cluster expansion model is the most accurate for any given speed. Or if you like, differently, if you want a certain accuracy, then the most fast model you can get is out of these, at least that we considered, is the atomic cluster expansion model. And just to put it in perspective, the classical force field model would be another factor of 100 faster. So, you know, they are roughly a factor of 100 less accurate, but also 100 times faster, the classical molecular mechanics force fields. So then the next thing that we looked at is something more challenging. So can these models actually learn a much more complex potential energy surface? So for this ACE linear regression, is it good enough? And so we looked at 3-BPA, which is a very, very flexible drug-like molecule. It has 3 dihedral angles that can rotate. It has 4 species, so it's really quite complicated. And we run molecular dynamics simulations of this at different temperatures, and then created 3 training sets and 3 test sets. And as you can see, the 300 Kelvin configurations have these very distinct pockets of stability. At 600, they are a bit more blurry, and then at 1200 Kelvin, basically it loses these and you basically end up sampling the entire space of the 3 dihedral angles. So what happens when you fit a potential on only 300 Kelvin configurations? So that means that you're only basically sampling a few spots in the dihedral space. So then what you end up having is a model that's very accurate at 300 Kelvin test set. But as you go to higher temperatures, ACE is the only model that actually, so for example, compared to SGDML, which is comparably accurate at 300 Kelvin, it becomes much, much more inaccurate at higher temperatures, whereas ACE is able to maintain this accuracy. And then so the ANI here refers to a reparametrization of ANI. So we have actually fitted ANI to this particular molecule, and ANI 2x is the is the force field that you can download from the website. And then this is the classical force field here as well for comparison. And then when we fit to mixed temperature, then the accuracy really improves on the entire potential energy landscape, and ACE remains the most accurate in this. And then we also wanted to look at sort of beyond this RMSE a little bit and see how the torsional energy landscape looks like. So we took slices at fixed beta. So we fixed this beta angle at 120 degrees, 150 degrees, and 180 degrees. And then we scanned through the alpha and the gamma angles. So basically we're rotating this group and obtained the energy along these rotations. And then we compared the different models to DFT. So we could only afford to do it with DFT at 3 different angles. And what we find is that ACE and SGDML seem to be the most accurate. And then, for example, GAP is quite blurry, so it's not really well regularized. It's missing a lot of features. ANI is really overestimating the energy here. So you can really see that only these two models are able to capture the main features. And then the red star shows the position of the global minima, and you can see that ACE is able to capture that. And the white dots on the DFT show where the training data is, and you can see that most of the landscape does not contain training data. So in some sense, this is again an extrapolation task where we are asking things from the model that it has not seen. And you can see that the sort of classical force field is really struggling with the subtle features. And it can get right a few of the main kind of points of the landscape, but then because it lacks the flexibility, it really misses, for example, entirely this big basin. So to summarize, I hope I could convince you that atomic cluster expansion is a good way of building organic force fields. It's fast and accurate for molecular systems. It's quite simple to parameterize using a least squares regression, and it also seems to show excellent extrapolation properties. And then with that, I'd like to thank your attention. I'd like to acknowledge a few people. So Cass and Christoph are the main developers of the codes. So the codes is the ACE and the IP fitting Julia packages. They are both available on GitHub. Gabor, who is really conceptualized the whole project and helping a lot. And then Giri, Alice, and Danny, they have helped with acquiring data for the 3BP and parameterizing the molecular mechanics force fields. And the rest of the group who are making work fun in Cambridge, and also AstraZeneca for funding. And I hope to see some of you in the poster session for a discussion. Thank you.
Thank you very much, David, for this nice talk. So we have one question from Simon Bassner. So go ahead, Simon. Thank you.
Yeah, thanks for this really, really great talk. Very interesting. Yeah, just one very detailed question. Is the MD17, is this the revised recomputed one or the original one?
So that's why I had the kind of line. So yes, on the left is the revised, and on the right, whatever we could find in the literature, basically.
Okay. Yeah, I'm asking because then part of the reason you see the big difference in the energies might be that the energies are noisy on MD17. They're unconverged, basically. But very interesting nonetheless. Cool. Thank you.
Okay, let's move to the next question by Claudio Zeni.
Hello, and thanks again for the really interesting talk and nice results. I have a very detailed question for you. What radial basis are you using in your ACE descriptor?
So I think it is the Chebyshev polynomials, but you can use any like orthogonal basis set. I don't think it makes much difference.
So the ones in droughts, the scale, the Chebyshev.
I think it's the same.
Okay. Thanks.
All right, that was a detailed question that got a detailed answer. I have a more sort of general question because you've shown us comparison between different methods, but can you get also a good feel of the reason why these different performances arise? Sometimes, always, rarely?
So I think so for these kind of extrapolation like results, we think that it's the regularized least squares regression is really one of the reasons. So the ACE kind of invariants are really probably quite good for describing these molecular systems. And then we think that the linear regression is one of the reasons that helps generalization compared to the non-linear models. But yeah, this is all things to be explored and confirmed, I think.
Okay, thank you. Thank you again, David. I think we are ready to move to the next talk. So that is Yasmin Bozkurt. Perfect.
Hello.
Great. So you have the floor.
Yep. Welcome again, everybody. I would like to first thank the organizers for giving me the opportunity to present our work. I'm Yasemin Bozkurt Güneş, and I'm a first-year postdoc at the Max Planck Institute for Polymer Research in Mainz, Germany. Molecular simulations are one of the, I guess, the areas that can most benefit from the developments in the unsupervised machine learning field, in my opinion. And just to give you an idea how, I would like to motivate with this classic timescale problem. In terms of the computational power, we are here-ish nowadays, but we are always interested in longer timescales. And there are a bunch of methods that allow sampling this region more effectively. And collective variable biasing is a way of doing this. The idea is basically picking some direction and biasing the system along this direction to accelerate the sampling. But this requires picking a good collective variable beforehand. And what is usually considered as a good collective variable in this domain is the one that allows crossing over the free energy barriers. In other words, separates the metastable states and characterizes the slow conformational motions, basically. To do that, people use, in general, their chemical intuition about the system and to choose these CVs. And some common choices are some angles, distances, contact map, coordination numbers, or some combination of these, or some highly system-dependent non-generic observables. And a good representation is not only useful in altering the dynamics in a controlled manner, but also for interpretation purposes, such as building kinetic models. And if the barriers are properly located in low-dimensional space, this will also allow obtaining a coarse-grained but accurate description of both the static and the dynamical properties of the system. For instance, when building Markov state models, which I think address the timescale problem in a different way. But unfortunately, how to obtain a good low-dimensional representation is a highly difficult task, and machine learning perhaps helps us to find one. Autoencoders offer a direct and easy route for such tasks with their special bottleneck structure and targeting the same input value after decoding by choosing basically fewer nodes in the bottleneck layer. We are basically forcing the network to learn the essence of the data and discard the irrelevant information, basically. And here, for instance, in this pictorial description, if you train the network with lots of cat images, the network learns the essential features about being a cat. So as the loss function, what's used is the discrepancy between the input value and the value obtained from the encoded and then decoded version of the input. And once the training is done, you can throw the decoder away and just use the encoder to perform the nonlinear dimensionality reduction tasks, thanks to the nonlinear activation functions used. And variational autoencoder architecture is a probabilistic spin to the standard autoencoders. Instead of just learning a mapping which outputs a single value from high D to low D, variational autoencoders enforce and also infer the parameters of the distribution for the data on the latent space. In other words, they learn to model data with structure. And with this approach, we represent each latent attribute of the input as a probability distribution. And when decoding from the latent space, we randomly sample from each latent state distribution to generate a vector as input for our decoder model, basically. And although the overall idea is very similar to the standard autoencoders, math behind is slightly different, and let me quickly mention. Now we are interested in finding the posterior distribution, meaning the probability distribution of the latent variable z given the input x. And it turns out that this direct calculation is not possible due to the marginalization needed to calculate the evidence. It's very hard. So instead, what is done is that we use what's called variational inference, hence the name variational autoencoders, and approximate this posterior with another distribution, say Q, that we define such that it has a tractable distribution, basically. Now we want to learn the parameters of this distribution. We can now reformulate the problem as an optimization problem, where we are aiming to minimize the KL divergence between the true and the approximate posteriors. And with some manipulations, the objective can be written as a sum of these two terms. The first one is another KL term that acts as a regularizer, basically that pushes the learned approximate posterior to the prior distribution chosen beforehand as close as possible. And the second one tries to maximize the reconstruction likelihood, in other words, minimize the reconstruction error. And this formulation nicely follows the neural network view as well. And due to the computational advantage in calculating the scale divergences, this prior distribution is mostly modeled as a unimodal Gaussian. But now these two terms come with a trade-off. And to understand the implications of a variational autoencoder and how it differs from the standard autoencoders, let's examine the latent space for this classic handwritten digits example. The left figure is when the network is trained with reconstruction loss only, which indeed becomes equivalent to a standard autoencoder. And by the way, colors correspond to different digits here. This mapping creates a bunch of points in the latent space without any structure. There is an uneven distribution of data within the latent space. In other saying, there are areas in the latent space which don't represent any of the observed data. And what's more, we don't know the distribution of the data there. And on the other hand, regularization loss alone does what it's supposed to do, actually pushes the embedding to a isotropic Gaussian and mixes everything together. And this basically treats every observation as having the same characteristics. So we fail to describe the original data. When both terms are considered simultaneously, we are in between. We map the distribution to something close to a Gaussian and also get okay reconstruction error and can visually separate the digits. And actually this plot is mostly used to motivate the use of variational autoencoders for generative purposes. As you see, there are no empty regions and we know the distribution of the data in the latent space. And the latent space is being actually easy to sample is important in the context of generative modeling. However, I would like to point out that if your intent is further cluster the latent space data for some further applications, it's not easy, I would say, to get clusters in the VAE spaces. In short, forcing the data to a unimodal Gaussian has an anti-clustering effect in the latent space, as the boundaries between the clusters are not clear and the standard clustering algorithms will mostly fail. I should mention that both standard autoencoders and variational autoencoders have been previously applied for conformational ensemble characterization. But we think that the unimodal Gaussian prior is not directly in line with the ideal free energy landscape view of biomolecules that contains well-separated metastable basins. And to address this issue, we suggest replacing the prior by multimodal Gaussian distribution, in other words, Gaussian mixtures. And we modified the loss function accordingly. The nice thing is that now the clustering is actually for free with this method because it performs the dimensional reduction and clustering tasks together. In which Gaussian the data belongs automatically determines its cluster. The number of clusters in the model is a hyperparameter. To clarify how our GMAE model works, I would like to give an overview on the architecture. First, the data points are probabilistically assigned to k number of clusters via a subnetwork, basically with a softmax, which is a hyperparameter again. Since each cluster is assumed to have a Gaussian distribution in the latent space, the mean and variance of each of these Gaussians are separately learned via the encoder part of the neural network. And we get the low dimensional representation Z by first sampling and then taking the expected value of these samples, basically. And the decoder part works very similarly to the encoder, but decoding starts from the individual clusters and the parameters of the latent space Z is learned, which is then followed by sampling. And another subnetwork follows in a similar manner and generates the reconstructed axis from each cluster. And then we again take the expectation to arrive at a single decoding. Overall, what we learn is the soft cluster assignments and decodings and a generative decoding mechanism, basically. And in the ideal case, all the probability values except the true cluster converges to 0, and the true cluster has a value equal to 1, which becomes closer to a hard clustering after a good training. We first check the clustering efficiency alone without any dimensionality reduction on the simulation data that we obtain from 1D forward potential system. And we just take the coordinates as inputs and train the network with 4 clusters. True labels are obtained by drawing these boundaries at the maximas, and the predicted ones comes from the GMVAE. And as you can see, the accuracy is quite high, and this lower left part shows the histogram values of the embedded space. So we can see that the original probability structure is preserved in the latent space. And here, this plot shows what we get from a unimodal variational autoencoder for comparison. As expected, due to the Gaussian prior used, it pushes the embeddings closer to each other, and this negatively affects the clustering. So with this example, Gaussian mixture prior seems like a good improvement over the unimodal GM standard variational autoencoders. Then we apply the method for molecular simulation data of alanine dipeptide, which is a simple model for conformational dynamics. And it is very well known that the motion is governed by 2 dihedral angles, phi and psi angles. And it is known that these energy minima correspond to metal stable states, basically, which have some separate special names as written here. And we will be using this Ramachandran plot to check our results. Here we train the network with pairwise distances between heavy atoms, augmented with the dihedral angles. And the left part shows the 2D landscape we obtained from our model. And we actually noticed a very interesting property of our method. Although we trained the network with 10 clusters initially, we got 6 from 0 to 5. All the other clusters were empty. So the GMBE method could be then useful in determining the inherent number of clusters, as long as it is trained with a parameter greater than the true number. And right part is the Ramachandran plot. And at the bottom here, you see where our cluster corresponds to in this plot, which match pretty well with the already known metastable state definitions. And we took another step, and using these 6 state coarse cluster definitions, we were able to build a Markov state model in these trajectories, which further sort of validates the suitability of the embeddings and also the clustering to characterize the dynamics as well. Now we are testing the method for a more challenging system, 15 residue long peptide. And in the simulations sample distinct secondary structures, coil states or fully extended ones relatively well, but the hairpin and helical structures are rare in this ensemble. Unlike the previous example, we don't have any information about the number of Gaussians needed. Plus, we don't have a reference kinetic model for this specific case. And the left part is what we obtained from our model. We identified 7 clusters. We first checked if the clusters are meaningful structurally by picking representative structures around the cluster centers. And these structures qualitatively suggest that as the cluster number increases from 0 to 6, the structure content becomes more extended. But we also did a quantitative investigation to verify. For that, we used several metrics because none of the metrics available perfectly separates distinct secondary structures. And this part shows the average fraction of helical segments, FH, and you can interpret it as it increases from 0 to 1. In other words, color goes from red to blue, structures become more helical. So for now, the cluster view and the FH calculation seems consistent. Cluster 0 is mostly helical and helical-like. Cluster 1 is containing more hairpins type, and the rest has coils in different extension levels. And as an additional test, we also look at the distance RMSD values. It is the average deviation of internal distances from the corresponding internal distances in a reference structure, which we chose as a perfect helical structure here as reference. So low implies helical and high implies fully extended structures. So all these results are in agreement with our conclusion. Therefore, for the helix coil transition, we were able to find good CVs. In our ongoing work, we have been studying on syndiotactic polystyrene, which exhibits a sorry for my pointer, exhibits some complex polymorphic behavior upon crystallization. Actually, it is a computational challenge to simulate the transition between 2 experimentally known polymorphs, alpha and beta structures, as this transition is extremely low. But our colleagues from the group, after iterating over different set of manual CVs, they were able to simulate the transition and obtain this landscape. For that, they have utilized the coarse grain simulations with 2 bead types, A for the backbone and B for the fennel ring. The left part of the landscape contains alpha type structures and right part is beta. And each form is further classified into other disordered forms, as you can see. The biggest struggle in this study was that there were tiny structural differences between these 2 polymorphs. So they had to really fine-tune these CVs to take into account for these small variations. They identified the variance of what's called SMAC, which take into account both local density and the mutual orientation of molecules. Here, the angle distribution between some transverse vectors. In short, they are extremely complex collective variables. To bypass this step, recently we have been working on to characterize such structures in a fully data-driven way. We use some local environment characterizing descriptors, which Michele Ceriotti showed in his phylogenetic tree of descriptors as input, and use the RGMVE method. This is still an ongoing work, but the results are initial results are sort of showing that we succeeded to separate distinct polymorphic structures within our GME framework. But we want to go further characterize and test if we can go beyond and further characterize the substructures and metastable states. In summary, for the representation learning problem, we propose to use Gaussian mixtures as the priors instead of the unimodal ones for the variational autoencoders purposes, because they handle the clustering and dimensionality tasks together. And we also showed that they could separate the metastable states pretty well. And for further details, our paper is available with an GitHub implementation. And I would like to thank Tristan Barrow and Joseph Rusunski for the GME work and Atri Bonerji for our polystyrene project. Also, I would like to acknowledge financial support from TÜBİTAK, the Scientific and Technological Research Council of Turkey, Koç University, and the Max Planck Institute for polymer research. So this concludes my talk. Thank you very much again for the opportunity and also for listening to me. I'm happy to take questions.
Thank you, Yasmin. We have at least 2 questions from the audience. The first one is from Eugene, who has the mic now, I hope.
Hello. So does the dimension reduction with the GMVIA include some kind of kinetical information, how fast the transition is in the local space?
No, we specifically didn't want to incorporate it because there are also some models that tries to decode the time lag version, which seems like a good idea in some cases, but for this initial implementation, we didn't want to do that.
Thank you.
Okay, thank you, Yasmin. We move to the next question, which is from Alessandro Laio.
Hi, can you hear me?
Yes.
All right. So how do you choose the dimension of your bottleneck? So so this to me always sounds like a complicated choice. I like your idea of the Gaussian mixture, but I haven't understood how you choose this other very important parameter.
Yeah, we wanted to actually keep it fixed to 2D in terms of the visualization purposes, basically.
So 2?
Yes.
All right.
Okay, it's a choice, I guess.
Yes,
well,
it was a choice.
Yeah, well, I would have a little bit to comment on this choice because in many cases, it's impossible to project your probability distribution in, the dimension that you can visualize, no? So there are many cases in which your system is intrinsically, for example, I don't know, 4-dimensional. And in this case, you unavoidably run into projection problems if you force the system to be 2-dimensional, right?
Yeah, you are definitely right. But as I said, we wanted to fix something and we decided that in order to compare with the other methods, we want to fix it to 2.
All right, thanks very much.
Okay, I guess you can continue this discussion at the poster session if you want to. And then Giovanni Settani.
Yes, thank you for the talk. Following up on the question by Alessandro, did you try to measure the fraction of variance explained of your autoencoder? How does it vary? Well, especially, you didn't change the dimension of the latent space, but it would be interesting to see how the fraction of variance explained changes as a function of this latent space dimension. Did you do anything in that direction?
Yeah, in the initial phases we did, but off the top of my head, I cannot give you some numbers, but it was pretty well for the toy models.
And for the multidimensional model, the 50-mer protein, did you do that?
No, actually, we haven't looked into that.
Okay, thanks.
Welcome.
Thank you, Giovanni. One last question by Sergio De Kerchi.
Hi, Yasmin. Thanks for the talk. I was wondering if you compared or would like to compare against things like normalizing flows.
We haven't done that yet. We compared with just standard linear models used in kinetic modeling, like TICA.
Mm-hmm. Okay.
and with all, of course, with the unimodal variation autoencoder as well.
Okay, if there are no further comments or questions from the audience, I think we can move towards the conclusion of the first part of this installment of the Mixed Gen series. Thank you again, Michele, David, and Yasmina, sorry, for the very nice talks and for being with us. I remind everybody that both David and Yasmin have posters in the Gather Town room. So if you want to go deeper in your discussions with them, that's the opportunity to do that. Now, my duties are coming to an end also as a host, but I still have the pleasure of reminding you again about our next events here online at SICAM, starting with the classics lecture in molecular and materials modeling, in which Tony and Dan will take us back to the origins of their method for free energy calculations for solids, and concentrate on the science. But, and this is the nice thing about this series of lectures, we will also have an informal session in which we are just going to ask questions like, well, were you drinking a beer when you first came up with this new idea that has stayed with us and become a classic method in our area. Then after this, we're going to close the season, or at least part of the summer season, and the Mixed Gen series with the last talk of the series that is going to be given by Alessandro Laio on estimating free energies from enhanced sampling to manifold learning, and this will take place on June 3rd. As we mentioned before, you can always find all the information about our events on the SICAM website. Go to other activities and then explore what's available there. And if you're interested, don't forget to register to our webinar mailing list that you can find at the bottom of various web pages, for example, at the bottom of the Mixed Gen session page. And with that, thank you very much for joining us. And I am looking forward to seeing you, albeit in this strange way via Zoom in the near future. Thank you.